let's take a look at how to compute eigenvalues, how to perform the eigen analysis. So we'll start from the definition. So what we will do is take a matrix and we'll say that S is an eigenvector with eigenvalue lambda and S is not equal to 0. And we will just write A is equal to lambda S, and we'll try to take lambda S to the left hand side, and we want to pull out S eigenvector. You want to pull that out, and then what do you get? You get A minus lambda times I times S. Why do we get I there? Because you cannot take A minus lambda because A is a matrix and lambda is just a number. So in order to be able to subtract it, you have to actually multiply by the identity matrix, and then you get A minus lambda I times S is equal to 0. That is the requirement for eigenvectors and eigenvalues. So, but what does that say? What it is saying is that some matrix A minus lambda I is some matrix times S equal to 0, where S is not a 0 vector. What's that saying? That's basically saying that that matrix that is multiplying S is a singular matrix, because a non-zero S multiplying that matrix is giving you 0. So the columns of the matrix are not linearly independent, they are linearly dependent. So it's a singular matrix. What do we know about singular matrices? We know that its determinant has to be 0. We know that the determinant of whatever is multiplying S here will have to be 0. So we can just write that, and now S has disappeared. There is no S there. The eigenvector is not there in this equation. And what is this equation? It's a determinant, and we know all the numbers in the matrix A, the square matrix, and we know all the numbers in I, it's just ones and along the diagonal. And lambda is the only unknown. N by n matrix, you can expand it along the top row, for instance, and it becomes a polynomial. So this determinant equation there, determinant equal to 0, is the same as a polynomial equal to 0. Is an equation that says a polynomial on lambda equal to 0. That polynomial, which is on lambda, is called the characteristic polynomial for the eigenvalues. If you can solve that polynomial, then you get all the eigenvalues. Theoretically, at least mathematically, that's how you do it. Practically, eigenvalues are computed using a completely different methods, but this is the mathematical way of doing it. A determinant equal to 0, determinant expands, and that gives you a polynomial equal to 0. A polynomial is on lambda, and just find the roots of the polynomial, and that's it. Those are the values, those are the eigenvalues. Okay, so we have to remember that this is the characteristic polynomial for the eigenvalues. By the way, the word eigen is a German word. It actually means characteristic in German. So what nobody calls it characteristic vectors and values in English. We use eigenvalues and eigenvectors. But for the polynomial, you don't call it eigen polynomial. At least I don't think people usually call it eigen polynomial. We call it the characteristic polynomial. But if you hear eigen polynomial, somebody calling it eigen polynomial, probably because he's got German heritage or whatever, know that this is what they mean. Just stating that the determinant of A minus lambda I is equal to 0, that is the polynomial. No, that's a polynomial equal to 0, so that's the equation. The left hand side is the polynomial. Okay, so let's actually apply this and see how it works out for the examples that we did earlier. So we take the permutation matrix, A is there, and if I take A minus lambda I, what that means is that I subtract lambda from the diagonal elements. So I get lambda there, minus lambda there, minus lambda there, wherever I see 0 along the diagonal. And if I expand it, what do I get? It's the determinant is lambda square minus 1 equal to 0. That is the characteristic equation. Polynomial here and the equation there. And the roots of that would be lambda square equal to 1. So lambda is plus or minus 1. Those are the eigenvalues that we got for permutation matrix. And in order to get the eigenvectors, we take one of them. We take lambda equal to 1 and just put lambda equal to 1 in A minus lambda I. So you get, wherever you see lambda there, you get 1. So minus 1, and 1 and 1. And you want this A minus lambda I times S equal to 0. How do you get 0 out of this? What kind of linear combination of the columns will give you 0? Just add them. So the vector that is multiplying this to get the 0 vector would be just 1 and 1. So take the first one and take the second one, add them, and that linear combination will give you 0. So the eigenvector corresponding to lambda 1 is equal to 1 is just 1, 1. Similarly, if you take lambda equal to minus 1, wherever you see lambda, you put minus 1. So you get 1, 1 and 1, 1. Matrix is singular. If you do Gaussian elimination, you just subtract the first row from the second, you get 0, 0. All those things, the second row is pivotless. But can you tell me why this guy is singular? Is it singular to begin with? And if so, why? It has to be singular because we found lambdas such that the matrix is singular. So when you take A minus lambda I for the solutions of the characteristic equation, you have to have singular matrices. Good. So here we get 2 eigenvectors in R2, which is pretty good. And we have R2 matrices 2 by 2 matrix. And we are looking for 2 eigenvectors and 2 eigenvalues. Very nice. Now we can see that these 2 eigenvectors, S1 and S2, are actually orthogonal to each other. If you just take S1 transpose S2, you get 1 times 1 minus 1 times 1. So it's 0. So the dot product is 0. So they're orthogonal. That is not an accident. It is because all real symmetric matrices have full set of orthogonal eigenvectors. Full set means if it is an n by n matrix, I have n eigenvectors and they're orthogonal too. Real symmetric matrices are the good members of the family of matrices. They're not quite the kings, but they are close to being the king. They're like maybe like the prince. Now let's take the projection matrix. So that is the projection matrix. By the way, is the projection matrix real and symmetric? So it is real and symmetric. It's obvious. It's right there. It's a diagonal matrix. And if I subtract lambda I from it, I would be subtracting lambda from the diagonal elements. So I get 1 minus lambda, 1 minus lambda, and minus lambda. And if I take the determinant, that would be just the product of the diagonal elements because everything else is 0. So I get that lambda times 1 minus lambda square equal to 0. Now I get lambda, the solutions would be lambda equal to 0 or lambda equal to 1 or lambda equal to 1. So lambda equal to 1 comes with a multiplicity of 2. And that multiplicity, because it is coming from the characteristic polynomial, is called the algebraic multiplicity. So lambda equal to 1 has an algebraic multiplicity of 2. Lambda equal to 0 has an algebraic multiplicity of 1 because it's only 1. It's not lambda square equal to 0, it's lambda equal to 0. With that, we can easily find the eigenvector because you just put lambda equal to 0, you get 1, 1, 0. And what multiplies 1, 1, 0? To give you 0 vector. So you have to multiply the first one by 0, the second one by 0, and the third one you can multiply by anything because that is already 0. So 0, 0, 1 multiplying this guy will give me a 0 vector. So that would be an eigenvector. Now about the other eigenvalue lambda equal to 1, if I do that, I can multiply the first column by anything, second column by anything, and the third column has to be multiplied by 0 because there's a 1 there, and then I get a 0 vector. That means my second eigenvector is some number and some other number, x and y, and 0 in the z position. Now, it is not just a vector, but it is actually a whole plane of vectors. It's a large number of vectors. Anything in the xy plane really is an eigenvector. So we can actually choose the vectors out of this space, subspace, that is the space of eigenvectors. Obviously, it's called the eigenspace for lambda equal to 1. So you can choose any 2 orthogonal basis vectors out of them. So the most obvious one to choose would be the x vector and the y vector, the unit vectors along x-axis and y-axis. If I do that, then those are orthogonal to each other. So I have to kind of modify my statement that said for a real symmetric matrix, you have a full set of orthogonal eigenvectors. What I mean is that you can choose vectors if you have an eigenspace, and choose vectors such that you have a full set of orthogonal eigenvectors. Now, the dimensionality of the eigenspace is called the geometric multiplicity because it's about the space. The good thing here is that the algebraic multiplicity is 2. The geometric multiplicity corresponding to the same eigenvalue is also 2. So 2 and 2, that is a good case. Now, the shear and rotation matrices, let's take a look at those. The shear matrix was that, and if I do A minus lambda I to get the characteristic polynomial and equation, what I get is in the diagonal, I get 1 minus lambda, 1 minus lambda, and 1 minus lambda whole square is equal to 0 because 1 minus lambda times 1 minus lambda minus 0 times 0.5, that is a determinant. So I get lambda equal to 1 and 1, similar to the projection matrix that we looked at, with the algebraic multiplicity of 2. So that doesn't bother us much. Now, if you put lambda equal to 1, you get that matrix because wherever you see lambda, you put 1, so 1 minus 1. And you can see that in order to get a 0 out of this matrix, you just have to take any multiple of the first column and the 0 multiple of the second column. So that is an eigenvector. But you cannot find another eigenvector. There's only one eigenvector here. There's no other eigenvector. But the geometric multiplicity is actually 1. So that is a bad situation. Saying that the geometric multiplicity is 1 is the same as saying that there's only one eigenvector. Shear matrix is a kind of matrix that does not have full set of eigenvectors, and that's it. So algebraic multiplicity is not geometric multiplicity. This situation is a bad situation. Now if you look at rotation, this is rotation for pi by 2 is skew symmetric, it's anti-symmetric, which means A transpose is minus A. And if you do the characteristic polynomial, which is the determinant of a minus lambda I, you get lambda squared plus 1. So lambda times lambda minus lambda times minus lambda, that is lambda squared, minus 1 times minus 1, that is lambda squared plus 1 equal to 0. So you get lambda is equal to plus or minus I. So we're stepping in the scary field of complex numbers here. And if you actually plot along and actually plug in the value I and try to compute the eigenvectors, then you get the first eigenvector to be 1 minus I, the second eigenvector to be 1 I, etc. So you get complex vectors also. So the vectors are in C2, not R2. So it is like the opposite of the symmetric case. In symmetric case, we had real eigenvalues, and real Q-symmetric matrices will have purely imaginary eigenvalues. Alright.